Good afternoon, everyone. Welcome to the second session of today. I'm Krishanu, and I'm coming from Shanghai Institute of Nuclear Physics in Kolkata. So before I go into the subject of my talk, I would like to first thank the organizers for inviting me and giving me the opportunity to present, one of my recent interests. Which is about anomalous Landau level, or anomalous energy quantization of Landau levels, in particularly under inhomogeneous fluxes. Of course, I will also be talking about homogeneous fluxes. So the main driving force for this work is one of my graduate students, Sergej. And some of the future work, we will have a postdoc at SINP, Surojit Bosak. Okay. So having said that, I think even though this is my first slide, the audience literally needs no introduction to this phenomena. It's a quantum Hall effect, which essentially gave birth to the modern topological phases of matter, as one of its applications among many, it sets a standard in precision metrology. So this is essentially one of the very early sign of quantizations observed in a physically measurable quantity when you expose a 2D electron gas to very high and uniform or homogeneous magnetic fields. Okay. So again, I'm not going into the details of this phenomena, as everyone knows about it. But the backbone is essentially set by the concept of having discrete energy levels, which are known as Landau levels. Okay. So essentially, what happens is that if you just take a simple quadratic dispersions, expose it to the magnetic field, you have equispaced energy levels, and the separation between these energy levels is not only dictated by the magnetic field, but also a scale that comes from the dispersion relation, essentially the inverse mass, for example. Good. So I think by now we all know that this kind of phenomena and Landau levels are no longer just taken as matter of curiosity, particularly among many of its other applications. They have been used as various designing principles, from protected transport, programmable band geometries, and particularly for in recent days, benchmarking quantum simulators. Okay? So the kind of quantum simulators that I'm referring to is essentially optical lattice models where this kind of Landau the Hall response has been observed in the system, and more recently this is a system of coupled superconducting qubits where essentially the Hall drift has been realized. Okay, this is a small geometry, but they have a very good control over the magnetic field, etc., where essentially synthetic gauge fields have been implemented. Okay, having said that, following some of the recent trends and moving from non-relativistic regime to relativistic setting, we all know now about the physics of graphene in great details. And people studied the kind of Landau levels that we realize in graphene. So essentially, when you expose this system to uniform magnetic field, what you essentially get is that a slightly different type of quantization than what we saw for the usual for the quadratic dispersion. But now, because you have a different dispersion, which is linear, you have a different scaling, okay, in the Landau level. These are no more equispaced. And you have zero energy Landau levels, and also other particle hole symmetric Landau levels. Okay? And that has now also been extensively utilized in improving the resistance standard, okay? Because graphene is extensively under investigation in various experiments. Okay, so essentially the take home is that if you want to understand this kind of phenomena across various dispersions, One method is to use the Onsager quantization, which essentially stems from the Einstein-Brillouin-Kähler quantization, and further refined by various other people, Roth and others. We now know that essentially the area perpendicular to the magnetic field in the momentum space is quantized this way. Okay. So, and this is essentially the Landau level index. You can see the scaling is proportional to the magnetic field, what you expect. This is essentially a topological contribution to the quantum, to this quantization, which is the Berry-Phase. Okay? So for graphene, it will come out to be pi. Okay, so using this formula, you can essentially write down this thing that if you have a general dispersion of the form E goes as k to the b, then you expect a Landau level quantizations of this form where En goes as n to the b over 2. It's a well-known result. So for example, if you set b equal to 2, you get the regular Landau level quantization. If it is linear in k, b equal to 1, so you get the graphene Landau level quantization. Okay? But importantly, whatever dispersion you use here, this b is positive. Okay, you can play with this further. You can apply an electric field along the confining direction, and you will see even for this regular Landau level, you do not see a linear spacing, but you get some other fraction coming up. But that is a positive number for you. Okay, good. Again, for this thing, as I already said, there was an intrinsic scale associated with the band structure, the inverse, the effective mass, for example. For this case also, that is not present, but instead the Fermi velocity plays an important role here. So for both the cases, you have an energy scale set by the dispersion of this underlying system. So given that, you ask the question that what happens if I do not have any intrinsic scale for my in the system that I am studying. Okay? So one good example where we lack such scales is a flat band. Okay? So we then ask that what happens if you sort of apply a magnetic field in a system that has flat band. Okay? So of course, if there is an isolated flat band, there is a trivial expectation is that nothing will happen. Okay? But then you can refine your question and ask that what happens if the flat band, instead of being isolated, is gapless. Okay? And it turns out there is a rich classification of gapless flat bands, not in terms of the dispersions, but in terms of quantum geometry. Okay? So I will try to explain this thing to some extent before I jump into the main results. Okay. Right. So the first thing you note is that, of course, the kind of semi-classical quantization that I am using here, that falls flat when you apply flat bands. So I do not expect to have quantized Landau levels for a flat band because I simply cannot define these the left-hand side here. Okay. So now it's a very brief introduction to flat band. Again, it's not quite necessary. But a very simple trivial manifestation of flat band is the atomic limit in the band theory. But it turns out that even if you include the particle hopping from site to site, it is possible to realize tight binding model where you have flat bands in the system. Okay? For example, here you can see there is one flat band crossing a quadratic dispersion band. You can tune these flat band. This is an example of an isolated flat band and then a quadratic band touching. This is even more interesting in 2D where these quadratic band is touching the flat band. Okay, that is where you get a gapless flat band. Okay, good. Okay, again, this is a very known statement that since the kinetic energy in this flat band system is quenched, we expect the interaction effects to be very dramatic. But even at the non-interacting setting, just the flat band is pretty interesting, even from the perspective of single particle eigenstates. Okay, so what are these? So this is, of course, if you take a tight binding Hamiltonian, you diagonalize that, you get the expression of the single particle states in this form. For a flat band, if you want to understand that what is the nature of the single particle, so of course, and you get extended states most generically, but for flat band, if you ask the same question that, what happens to the structure of the eigenstates, because of this particular construction that, flat band eigenfunctions are a finite sum of the block phases, it turns out that this coupling is strictly restricted within a unit cell. Okay, so what it means is that your eigenstate will look like a localized state. Okay, there is no disorder. You still have a localized eigenstate, and this kind of localized eigenstate is called compact localized eigenstate. Okay, so given a flat band, and if you do a simple Hilbert space counting, you should be able to construct n linearly independent copies of this eigenstate if you have n such states on the flat band. Okay. Now it turns out that is not always possible when you have a gapless flat band. Okay. So that essentially set the stage for our investigation that if you have a gapless. Sorry.
Gap flat band, but if it doesn't have the trivial topology, that means it has some Chern number. So gap flat band with Chern number, then I think that you do not able to have the compact localized state. Yeah.
No, it is no more a perfect flat band.
Right. So even even with the flat band, but it gap flat band, but let's say you have non-trivial topology, then I think that compact localized state cannot be achieved.
No, exactly. Yeah, there is a no-go theorem which essentially says that you cannot have compact localized states when you have a Chern number in that. Yeah. Any other question? Okay. Okay. So right. So the kind of setting that I'm interested in is that you have a quadratic band touching and a flat band, and it is possible that when you are writing down, these the Gram matrix, for example, or the copies of these compact localized states, you ask the question whether it is possible for you to construct linearly independent compact localized states. So it turns out, given the gapless point, it is not guaranteed that you will be able to do that. So there are two classification. There is a classification that essentially reveals two classes. One, which is called a singular flat band, and the other, which is called a non-singular flat band. So for the singular flat band, it turns out, if you construct this matrix to characterize the linear independence, that has a vanishing determinant, because one of these alpha k that I showed in the previous slide, which is appearing in the coefficients of this expansion, that can be 0. So that means there is a singularity. That matrix is non-invertible matrix, and for that we call this kind of flat band to be singular flat band. But then, if you can write down a smooth projector onto the flat band for certain other gapless flat bands, we call that to be non-singular flat bands. So essentially, whether you are able to write down a smooth projector onto the flat band space or not, we classify that in two different classes. Okay, one is singular and one is non-singular. So there is another characteristic to understand that where is this singularity coming from, and that turns out to be the quantum geometry, which I will talk about. But even very naive, distinction between these two cases is that if you try to gap out the gapless flat band, for the non-singular band, this trivial gapping out is possible. Okay, for the singular flat band, this is not the case, and particularly if you break time reversal symmetry, in a singular flat band, we'll always acquire Chern number that we were talking about, but that is not guaranteed to be the case for the non-singular flat band. Okay. So, having understood this classification, we now move to the response of this kind of systems when we expose them to magnetic fields. Okay? What has been understood so far is that if you expose a non-singular flat band to the magnetic fields, what you see here is, of course, the appearance of Landau levels. But essentially, so for these calculations, I'm always setting the flat band to be at 0, okay, just for simplicity. And you see that there are regular kind of Landau levels. So, of course, if you are very far away from the gapless points, you expect equal spacing between the Landau levels. That's what it was expected. close to the degeneracy point, you have that spacing is not maintained. Again, that is what you probably expect. Essentially, there are no further Landau levels in these systems. Okay, but now if you do the same calculation for a singular flat bands, something more interesting happened that you cannot explain entirely in terms of the dispersion parameter. Okay, so for example, when I talk about the dispersion parameters, these are the different effective mass components that comes from a dispersion. Okay, so for this kind of Landau levels, okay, the entire Landau level quantization can be understood entirely for in terms of those parameters. Okay, but for a singular flat bands, what it turns out that in the free space available in the energy landscape, we find additional set of Landau levels. Okay, so you do have the positive branches of the Landau levels, like what you have for the non-singular case, but you have an additional negative branch of the Landau levels, which is forming below the flat band. Okay, and the scaling of these Landau levels cannot be explained in terms of the dispersion parameters or the effective masses. Okay, and it turns out this is rather dictated by the quantum geometry. Okay, but before understanding this thing, if you just ask the question that what is the quantizations of these Landau levels, which are additionally appearing for a singular flat bands, the answer turns out to be this. Okay, that your Landau level quantization is inversely proportional to the counting index. So these kind of Landau levels are termed as unconventional Landau levels or anomalous Landau levels. The anomaly essentially comes from the fact that you have a Landau level quantizations. Sorry? Unconventional Landau levels. Unconventional. Yeah. So essentially, what it means is that you have a n to the alpha quantization, but alpha is not positive. Okay. Okay. So right. So what we found, or what people have found, is that the prefactor in this quantization is strictly dictated by these this parameter, which is called quantum distance. Okay, I will tell you what that parameter is essentially. And again, as I said, the dispersions do not fully characterize these quantum dynamics here. Instead, you need more geometric information beyond the regular dispersion relations. Okay, so a very brief introduction to the kind of quantum geometry that is relevant for us here is that this is one of the fundamental quantity in understanding quantum geometry in block bands. It is called a quantum geometric tensor. Of course, I guess most of you are already familiar to that. It essentially characterizes the parallel transport of block wave functions or the block bundle in that sense. Okay. So from this quantity, yeah. 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 Exactly. I will come to that towards the end of that. Okay. So from that, one can derive two fundamental quantities. One is called the quantum metric that comes from the real part of that. Okay? And the other is the imaginary part, which is known as the Berry curvature. Okay, so one essentially talks about the stretching and the other talks about the twist in the block bundle. Okay, so now if you, from this metric, you can define a distance, and this distance is called the Hilbert-Smith distance. Okay? And it turns out that it is this distance, or rather the maximum of this distance around the gapless point is what gives you the prefactor for this anomalous scaling. Okay. So a very simple way to understand is that you essentially have, so if you take this Hamiltonian, then at the Hamiltonian which you can solve to get this kind of the Hamiltonian that essentially gives you the gapless flat bands. If you take that Hamiltonian, apply magnetic fields, and you go to the number operator basis, which is the usual way of calculating these Landau levels, then you find that essentially this kind of spreading happens due to the band mixing between the Landau levels of the flat bands and the dispersive band. Okay? So that is why you have this level repulsion, and you have the appearance of these anomalous Landau levels. Okay. So now, again, in what I just explained, so a glimpse of the model, the kind of model that
in the previous slide, the theta is the angle in the momentum space.
Yeah.
Okay.
Yeah. And you calculate the maximum of that angle essentially, which gives you the maximum distance. But there is a relation of that angle with the distance. It's a monotonic function of that, and that is what.
Yeah, but I guess the metric also depend on not only the angle but also on the radius.
No, it does not depend on the radius actually. It just depends on the angle essentially.
That's true. Because like I don't know about your exactly model, but for example, like fractional churn insulator, the metric is depend on both the coordinate like kx, ky. So it's also the angle.
Okay, yeah. So I think, yeah. So for an isotropic case, yes, it does not depend on the radial thing. For an anisotropic case, what I'm taking is the maximum of that. Okay. So you maximize with respect to the thing for a given thing, and that is what happens.
Okay.
Yeah. Yeah. Thanks. Thanks for this question. See, what I am essentially calculating is that I'm taking, so I have this gapless band. I'm taking two K points. Okay. You can take them to be diametrically opposite, crossing through the gapless points. And I can calculate the distance between them, psi K1, psi K2. And I'm rotating. So essentially, I'm maximizing that distance with respect to theta. So yeah, so this is not coming directly in the calculations. It is rather this which is appearing from this. Yeah, because I cannot define the imaginary part here. But you have a gapless point, right? So that will divert. Okay. Okay, so nothing to be scared of. So this is essentially the minimal model that can give rise to a singular flat band. Let me explain these parameters. So if you take, in principle, if you take a Kagome lattice, include nearest neighbor and third neighbor interactions, you can derive this kind of model by expanding around the gamma point as long as your flat band is protected. Okay. So, in this model, essentially, these parameters A1, A2, A3, A4, these are the band parameters, and you can define the quantum geometry entirely in terms of these band parameters, okay? Particularly the maximum of the quantum geometry. So when you have a singular flat band, okay, we still call it like a strongly singular flat band versus weakly singular flat band, because if you calculate the quantum geometric marker that I showed, if that marker is very close to 1, which is the maximum value allowed, we call it a very strongly singular band. If it is very close to 0, it is weakly singular band. If it is 0, then it's non-singular band. So for this model, one assumption is that one of these parameters, particularly A1, is non-zero. You can set the A2 and A3 to be 0, and essentially the other parameter A4 dictates the quantum geometry in this system. Okay? So that gives you the minimal model to understand the physics. If you apply this model, if you now add magnetic field, perpendicular magnetic field, you can brute force solve this two-band system, and you can write down this kind of quantization there. Okay? So it will turn out that this is the quantizations around the flat band energy, And you can simplify that under the condition that I was talking about, one of these, these strongly singular limit or weakly singular limit. In either case, what you get is that this simplifies to this d max square over n, which gives you both the scaling as well as the prefactor that is coming from the quantum geometry. Good. Okay, so having understood this continuum model a bit, we wanted to see what happens when you have a lattice. Okay, and since we know that the flat band in the Kagome lattice is a singular flat band, so we took this Kagome lattice model and exposed two magnetic fields. Okay, but here we included another important parameter. So essentially, if you see that we are allowing different flux concentration on different plaquettes. Okay, keeping the total flux within the structural unit cell constant, I can essentially tune alpha or xi. Particularly, if I fix alpha, which essentially controls the flux density, I can vary xi to control the flux distribution. So, for example, here, if your xi equal to 1, this corresponds to the uniform magnetic field case. So essentially, you have 6 alpha amount of flux here and alpha amount of flux here in each triangle. And we are now tuning this xi parameter away from 1 to introduce the inhomogeneity in the flux distribution. Okay? And I will show you there is an interesting limit, which is xi equal to 0, in which you have essentially no flux in the triangle, and all the flux is concentrated only in the hexagons. Okay? Okay, so with this flux distribution, you then ask the question, what happens to the anomalous scaling, okay, that we got here. Okay? So what I'm doing now, I'm plotting the anomalous quantization as a function of these parameters xi. Okay? And what we get is the following. So when you have xi equal to 1, that is the uniform limit. And you can see that you have a very well-defined anomalous quantization here. And this holds even when you are moving away from xi equal to 1. Okay? So essentially what is happening is this entire tower of anomalous Landau levels is getting collapsed. Okay? Now, as a function of xi, you see that there is a special point, which is xi equal to 0, which I said that all the flux is concentrated only in the hexagons. And by the way, when I'm doing this variation, I'm keeping the total flux content of the structural unit cell to be fixed so that there is no addition or enlargement of the magnetic unit cell. Okay? So if you do that, if you essentially do this kind of flux redistribution, you find that this special point, there is a special point at which all the Landau levels completely collapse to form a massive degenerate space of Landau levels at E equal to 0. And there is no other states below E equal to 0. Okay? So, so we want to understand what's going on here. So it turns out that in a leading order approximation, this collapse is almost linear as a function of these parameters xi. So essentially what is happening here, this anomalous quantization is xi times d square over n, okay? Because the d square has always been there for any value of xi, but at xi equal to 0, all the Landau levels are at equal to 0. Okay? So we, no, at some point this adiabaticity will not hold because there's a very dense, dense energy of these Landau levels. Okay. So then we asked the question that what is happening at this special point, xi equal to 0. Okay? So it turns out that at xi equal to 0, your magnetic block Hamiltonian is entirely positive semi-definite. And that is why you do not have any negative energy spectrum. Okay? And moreover, there is an emergent supersymmetric quantum mechanics that you can, or a supersymmetric algebra at this xi equal to 0, that you can think of to be present in this system and generated by this generator, okay? So now those who are familiar with the supersymmetric, simple Witten's supersymmetric quantum mechanics, you know that it is essentially this algebra that you take the generator of this supersymmetric algebra is a fermion odd operator. And when you square it, essentially, you get a supersymmetric Hamiltonian that commutes with this charge operator. It's generating the symmetry transformation. There are additional pieces in the algebra that are not so relevant here. But what it turns out that if you look at these two pieces, our Hamiltonian is essentially of this form. Okay? So when you have this Hamiltonian, the magnetic block Hamiltonian, you can write down it either as R dagger R and RR dagger. Okay? Now this composition is not just any composition for us, but it is important to note that the kind of R matrix that I'm showing here, it has the same degree of locality as the Hamiltonian itself. So keeping the locality intact, I'm splitting my positive definite Hamiltonian in terms of either RR dagger or R dagger R. Okay.
So what's the C and B here?
So this, yeah, good question. So the C and B are so to understand this algebra, C are the fermionic operators, B are the bosonic operators. But for me, the C and B can essentially be thought as two different lattice sides of a bipartite lattice. Okay. So in that sense, Q, this Hermitian form of Q can be thought of as a block Hamiltonian on a bipartite lattice, which I'm squaring to get two distinct Hamiltonians. One is R dagger R, and the other is RR dagger. Now, you know that in supersymmetric quantum mechanics, there is an exact energy correspondence for all finite energy eigenstates. So all non-zero energy levels are doubly degenerate. That is expected from the structure of RR dagger and R dagger R, but the zero energy manifold can be different. Particularly when R is a rectangular matrix, if you have a different set of different number of fermions versus bosons, or equivalently different number of A lattice sides versus B lattice sides, you expect to have additional zero modes coming from the null space of R and R dagger, coming from the difference between the null space of R and R dagger. And this difference is essentially what we call the Witten index in the supersymmetric quantum mechanics. Here, it turns out that this Witten index is exactly the number of flat bands that you realize in one of these Hamiltonians. Okay, good. So, so the number of the zero modes that we got there in the previous plot, you can have an exact count of those zero modes using this index theorem essentially. And you can you will know that what are the number of anomalous Landau levels you are having in this system. Okay, it turns out that if your flux concentration is P over Q, you essentially have Q number of zero modes in the system. Okay, so okay, so let me now understand these lattice correspondence, these spectral correspondence between the two magnetic Hamiltonians in terms of this Hofstadter spectrum. If you study the Hofstadter spectrum for this model, so our model, we find this Hofstadter spectrum looks like this, the Kagome model. You can see that there is a set of zero modes here in the Hofstadter spectrum, and if you remove that zero modes, it looks exactly identical to the Hofstadter spectrum that we realize in graphene. Okay, so that is precisely the lattice correspondence that I just established in the previous slide, which we call this lattice supersymmetry. So again, the things to read here is that you have additional set of, so when you have a flux configuration, which is given by, with strength given by P over Q, you have exactly Q number of anomalous Landau levels at zero energy, which are not present in the spectrum of its partner. This middle thing is essentially the block Hamiltonian of the charge operator, okay? And this represents a different lattice. Okay? I'm not going into the details of that thing.
So basically, in this case, your supersymmetry is just some kind of like matching between the energy levels rather than mapping from boson to fermion, right?
Yes, exactly. Yeah, exactly. Okay, so this also gives us to construct a lattice analog of a very old theorem which is called Aronoff-Kashad theorem, which taught us that you can have a manifold of zero modes. Okay? With the degeneracy determined solely by the flux density. Okay? And so here we find that we have a very similar situation on the lattice. So we are calling it a lattice analog of this Aronoff-Kashad theorem, that your flux density decides the degeneracy of the anomalous Landau levels at zero energy. Okay? Because the underlying operator algebra is the same. The calculations that we did here is the same type of calculation that Aronoff and Kashad did there in their work. Another point to mention here is essentially we find the phenomena of a partial Aharonov-Bohm caging, which was initially proposed by I think Benoit and with Julien. They're all there in the audience. So, but one important distinctions with this thing is that so for them it was a uniform special flux distribution, and what they found is that all bands are flat. That is what they termed as Aharonov-Bohm caging. For us, it is a partial Aharonov-Bohm caging, so you can still construct the kind of compact localized states that we find in the presence of this magnetic field. And the trade-off is that you can realize this in inhomogeneous magnetic fluxes, okay, not just the homogeneous magnetic fluxes. Okay, and this is again, it's mandated by the supersymmetric algebra that I just showed to you. But one important fallout of this thing is that the kind of zero modes that you get here, or the flat band that you get here, is pretty robust to certain disorders, and disorders both in the hoppings as well as in the flux configurations. So because you know that there is an underlying Q charge operator, which is a magnetic model on a different lattice, you can go there and apply whatever form of disorder you want. When you square it, you will always get this type of bands there for the Kagome model. Okay, so this the set of zero modes are sort of protected to a large class of disorder in the flux configurations as well as in the hoppings. Okay. This is not the case for the uniform case. For the I think I am almost closing. So for the uniform case, what we found is that if you have a weak disorder in the system, of course the scaling is still pretty visible, and you see deviations when you increase the disorder strength in the system. Okay, so you have some form of the collapse in the presence of disorder, but the zero mode is pretty robust. Okay. Right. So so we can understand this evolution as a function of xi by studying this quantity, which is called an age locality marker. So essentially, you try to understand what is the density of the age states in a finite system, and you do find that for the uniform case, there are major gaps in the Hofstadter spectrum which host age modes. And if you tune the xi, sorry for this color bar here, but essentially there is a density of high density of zero modes at the xi equal to 0 that you can see here in these via this age locality marker. Okay, I think the last thing which I want to show here is the transport. Of course, if you calculate the transport for these anomalous Landau levels, and what we found here is that you can see the spread of the Landau-like bands in this system when your Q is very large. So if you calculate the Berry curvature for these systems, you see they are reasonably flat when you are away from the zone boundary. And for that, if you calculate the Hall conductivity here, you can see that this changes in steps of 1, which we expect from the regular Landau levels. Okay. And also you can make a plot as a function of E. So essentially to the point that you can resolve these Landau levels, because you have very high density as you go to E equal to 0, you see that this kind of clean Fermi-like Landau levels appear. Okay. Okay, I think I'm almost towards the end of my talk. We, of course, it's very difficult to understand this kind of flux configurations in a real system. So of course, we asked that can quantum simulators offer any respite for us? And we know that particularly this Kagome system has been realized in optical lattice model, and quantum Hall effect has also been observed in optical lattice systems. Given that, we pose these questions that whether we can understand this kind of inhomogeneous flux-induced phenomena in this quantum simulator platform. And these are the practical challenges that we have in either platform, but we are trying to, we are in conversation with the experimentalists in TU Munich to see that whether superconducting quantum processor can essentially be useful to understand this. I think these are some of the other routes that we are taking. We will be understanding essentially the case of multiple flat bands, because you want to understand that what is the role of quantum distance when you have multiple flat bands? What is exactly the coefficient that appear in the anomalous Landau levels when you have more than one flat bands? and of course, the effect of interactions in these systems. Yeah. With that, I would like to.
Okay, let's thank Krishanu again. Questions, please? Any questions? There must be mics in each row.
So, is it working? Yeah, okay. So at some point you were mentioning that part of the analysis was based on K-space.
Yeah.
But finally, it seems that many ingredients that you show at the end of the day was done in real space. So, so can we think about studying other models which might not be periodic or
sorry, what? Other what? Sorry.
Models for which the geometry is not periodic?
We are thinking of doing that. Yeah, particularly, I think the kind of lattice supersymmetry that I showed to you is expected to hold in, for example, this hyperbolic geometry, where your conventional block theorem will not apply. So you have, non-abelian version of block theorem, as well as quasi-periodic systems where your K-space description is not valid.
And so for hyperbolic geometry, for instance, you have some results already?
Not yet.
No.
We are still setting that up. Yeah. Yeah.
So first, you've shown that there is this quantum geometry that controls the spread of this anomalous Landau level.
Yeah.
And you have shown that when this psi parameter goes to 0 in the Kagome lattice, all the Landau levels collapse. But I was wondering, are there some situation if what you call Dmax vanishes?
No, it's not exactly the Dmax vanishing case.
Yeah, exactly. So, because on one hand, there was a criterion based on quantum geometry and also supersymmetry appeared later, but are these two notions sort of...
Yeah, I mean, you were right. I mean, one way to make them vanish is to essentially take the Dmax square continuously to 0 by tuning the band parameter. But for us, Dmax is finite for all these things. I mean, we're not playing with the band parameters. This is the flux distribution that is controlling the effective quantum geometry for us, such that you have a different mechanism to make the Landau level collapse.
Okay. Well, actually, one possibility would be to take you could study a geometry with the same psi parameter, but with 0 average flux. So maybe you would have a band structure because then translations commute. So you would have and maybe this is the relevant quantum geometry that you need
I see.
to
So
take
you're
into
saying
account.
if you have the total flux to be 0 in
Exactly.
in each structural unit cell, so your magnetic unit cell is essentially same as the structural unit cell.
Exactly. So you could have a staggering of the flux with a really very inhomogeneous pattern. Then you would get quantum geometry reflecting the staggering, and maybe that the two notions would be reconciled.
I see. No, yeah, that's a very good suggestion. See, I haven't thought about it, but yeah, thanks for this for pointing this out. Yeah.
Okay, let's thank again and move on to the next talk.